Hello guys, I'm Naveenraj and today I'm going to talk about my research topic XS1-L01A-TQ128 by XMOS. This research was guided by Mr. Professor Dhanabal R for the subject Computer Organization and Architecture. The XMOS XS1-L01-TQ128 is a powerful device that provides a simple design process and highly flexible solution to many applications. It contains a single X core tile, of which we'll talk about later in the upcoming slides. It also uses a set of software components that are rapidly customized and composed. We can also use high-level languages such as C and C++ to program the device. To add on, XMOS introduced a tool chain along with the microcontroller, which consists of compilers, simulators, debugger, and a static timing analyzer. So, to know more about the microcontroller, let's look on to the answers for some questions to fire up the research. Yes, the first question is to draw the clear block diagram of the microprocessor, microcontroller, or the IP core selected. And here is the given block diagram of XS1-L01A TQ128 by XMOS. As said earlier, the microcontroller um, consists of a single X-style core, which means there are 7 cores, 7 logical cores from 0 to 7, and there are 32 channel ins, um, 6 clock blocks, 10 timers, 4 clocks, 7 synchronizers, JTAG, boot ROM, security register, and OTP port. And let's discuss one by one briefly. The Xcore tile has up to 8 active logical cores, and this logical cores um, issues instructions down a shared 4-stage pipeline. The 4-stage pipeline, and it shares the instructions around here. Yeah. So the instructions from the active codes are issued round robin in no particular order. So if up to 4 logical cores are active, each core is allotted 1 by 4th of the processing cycles. Suppose if more than 4 logical cores are active, then at least 1 by n cores are allocated for each processing cycle. These cores, synchronizers, and logs are all responsible for the performance of the microcontroller. Now let's talk about the logic channel ends, links, and switches. Logical cores communicate using point-to-point communication formed between the channel ends. As you can see, there are 32 channel ends, and the logical core communicates using only these 32 channel ends only. Okay, so these are implemented over X connect links and routed through switches. Something called X connect links, and these links are routed through the switches here. The links operate in either 2-bit per direction or 5-bit per direction, depending on the amount of bandwidth required. Okay, so streams provide the fastest possible data rates between X core tiles, which is up to 250 MB per second also. So that much fastest data transfer is possible between X core tiles is because of streams. So all packet communication can be multiplexed onto a single link. A total of 4 5-bit links are available between two cores. There are 0 to 7 cores, and there will be totally there will be totally 4 5-bit links. So this this cores communicate using channel ends, and the channel ends are routed through with the switches. These all are connected using X channel links. and between each core there are 4 5-bit channel links. Yeah, that's all about links, ends, and switches. Now let's talk about ports and clock blocks. So ports provide an interface between the logical cores and the I/O pins, input/output pins. Okay, signals in different directions cannot be mapped onto the same port. So all pins of a port provide either input or output. So the operations of each port is synchronized to a clock block. There are totally 6 clock blocks, and um, the ports operation are synchronized with these clock blocks. This clock block can be connected to an external clock input, or it can be run from divided reference clock. Yeah. This port and the links which is saw in the above section, these links I'm talking about, the links X connect links which runs across the cores and the channel ends and the switches. So these links and the ports are multiplexed because for allowing the pins to be configured for use by ports of different widths or links. So suppose if a port is enabled, it overrules ports with higher widths that share the same pins. So there are no ports don't have unique pins. Suppose a port is enabled, it just overrides the other port, sharing the higher bandwidth, sharing the yeah higher bandwidth, higher widths. Um, the pins on the wider port that are not shared remain available for use when the narrower port is enabled. So a port which that the sizes of the port will vary, wider port, small port, and suppose they might share the same pin. The pin selection depends on the data transfer rates now. Ports always operate at the specific width, they even if they share same pins with another port. So they don't change their width. A port is assigned with a particular width. The width is not variable at all. Yeah, that's all about the ports and clock blocks. And timers are 32-bit counters that are related to the X code tile. It's defined to tick every 10 milliseconds. Okay, so this value is derived from a reference clock which is configured at 100 megahertz by default. We can change the default value applying codes and all, but default it is 100 megahertz, and this timer ticks at every 10 milliseconds. Okay, that's all about the timers. Timers don't have that much significant in the block diagrams, but while programming, the timers play a significant role in for loops and controlling operations, logical operations and all. This is the PLL. The PLL creates a high-speed clock that is used for the switch, dial, and reference clock. The PLL multiplication value is selected through the two mode pins. There are two mode pins that will select, uh, and that can be changed by software to speed up the tile or use less power. So this consumes power because high speed clock is being set, right? So this can be changed using the programs. So by default, it has some value. Um, suppose there's some oscillator frequency, X frequency, and we have some a tile frequency. Based on this, the PL ratio is set, and there are some PL settings too, OD, F, and R. That's just out of scope, but there are the OD, F, and R values can be modified by writing to a digital node PLL configuration register. There's something called PLL configuration register, and these values can be changed using writing to these nodes. Okay, so that's all. Now let's talk about the boot ROM. So talking about the boot ROM, it runs a simple operation. We go step by step. Suppose there's a primary port, and in that boot we'll be setting each bits of the security register. We'll talk about the security register in a few moments. So suppose if the bit 5 is not set, Then we again boot it according to the source pins. So we'll assume the bit 5 is set, which means bit 5 equal to 1. The security bit 5 is 1. So now from the OTP port, the contents are transferred to the base of SRAM, and the program gets executed. This is the basic function in layman's term of the boot RAM, of the boot ROM, sorry, uh, boot ROM, read-only memory. We can't change it. That's why it's called read-only memory. There are different modes, boot source pins 0, 1, 1, 0. So there are many modes reserved. Exponent link B. There are many modes, and that depends upon each microcontroller or microprocessor. It depends on the manufacturer. So we just spoke about the OTP register, right? So what is that OTP? It's a 8 KB one-time programmable memory along with security register that configures system-wide security features. The basic security features for the whole scale of the system, of whole scale of the microcontroller, is configured by this OTP port. Okay, so it holds data in 2K rows and 32-bit configuration. The additional data in OTP is copied from the OTP to SRAM and executed as the first on the processor. So the first program executed will be from the data is the boot program that executes first. Okay, so the data from the OTP register, OTP memory, along with some security register values, is transferred to the SRAM base of SRAM, and then the program is executed. This security register has many features: a secure boot, disable JTAG, disable link access. There are a lot of security features, and this just specifies the access and how the boot program should get executed. The main focus is to execute the boot program securely, and for that we use this security registers, and this comes along with the OTP. So OTP plus security register, this goes to the boot ROM, and goes to the SRAM base of the SRAM, and the program gets executed. So this all is seen as a whole. We don't split it into parts and see. Security register contains so many features. It will disable JTAG, which we'll see what is JTAG in the coming in a few moments. And yeah, OTP security register, and it goes to the boot ROM. So now let's talk about the JTAG. So boot ROM. So now is JTAG. JTAG can be used for loading programs, boundary scan testing, in-circuit source level debugging, and programming the OTP memory. So yeah, it consists of so many pins. TRST underscore N pin, debug N pin. There are a lot of pins, and yeah, it is used for boundary scan testing and loading programs into OTP registers and all. Um, the user code can be read using the user code instruction. JTAG's user code can be read using user code instruction. There's an instruction for this particular MCU, and its user code can be read using the user code in all in caps. Okay, so that's all about the JTAG. That doesn't have so much insignificant over the MCU when compared as a whole, but when you go when you go deeply into the block diagram, it plays a small role, definitely. So talking about the PCU, it can be used to isolate the core voltage of the device and reapply it under a controlled condition known as sleep mode. In sleep mode, all data in the SRAM is lost. SRAM doesn't store any data in sleep mode. Okay, so the device recovers into functional mode under the control of an external signal. So this signal is called PCU wake signal or an internal timer. Okay, so this data is recovered using this signal. Okay, So if PC is not required, PC should be left unconnected. This is not required all the time. People don't use it all the time. Suppose if it is required, then this is the process happening. Doesn't play a big role uh, in the whole microcontroller. And there are a lot of power supplies pin, VDD, VDDIO, OTP, VCC. There are a lot of power supplies pin and requires quite sufficient power for powering the microcontroller. And yeah, I guess that's all about the whole block diagram we've seen. And now let's go to the second question. Next question is about the instruction set. This refers to an opcode, a code which will perform a particular instruction. Okay, this is just normal. It is available in all data sets and it has some particular function. And while coding, we use such instruction sets to make a function or to make a function. That's it. There's nothing to talk over these instruction sets because it's just a common thing which is there for all the data sets. Suppose example PC is the program counter. Everyone knows that. SR is status register. SP stack pointer. DPTR data pointer. It just the code just varies between microcontrollers and manufacturers, but the functions don't vary. Suppose the stack pointer performs a function in this in XS1 XMOS microcontroller, and the same with 8051 microcontroller, CT89 microcontroller too. So it's the same thing, but just the code varies. It's DP here, and for CT89 PVD51, that microcontroller is DPTR. So it just that's just a code varying. This is again the continuation of the second question, the instruction set and pros and MUL multiply. Div U is div unsigned. Div S is div signed. Div signed. Rem U is reminder unsigned. Rem S is reminder signed. It's the same thing which we see. It's just the same thing. We easily get to know coding for the programs and all. So let's see what's the clock cycle. It's all have a single cycle execution. So each instruction has a single clock cycle execution. Therefore, the clock cycle required is one. Um, at the given data sheet, the memory required will be uh, 64 kb's internal single cycle SRAM for code and data storage, 8 KB internal OTP for application boot code. Just simple. It's just about the instruction sets. We go to the third question. That'll be interesting. Talking about the third question, it's explain microprocessing element and its architecture. So as we saw in the block diagram itself, so briefly, so in detail. So the microprocessing element it just contains a single X core tile, so which has 7 logical cores with switches and links, X connect links. So that's given here, and it follows RISC architecture. That's very important, and it's 500 MIPS shared between 8 real-time logical cores, and there are 16 32 bits dedicated registers, and 159 high density bit instructions. So these are instructions, and similarly we have 139 high density instructions. Okay, and there's something more important, that is it has 64-bit MAC instructions for DSP, digital signal processing, arithmetic, and user definable cryptographic functions. So cryptographic functions are responsible for the security of the microcontroller. It just encrypts and decrypts data transfers and all. That's really necessary in concern with the security. Now let's directly jump to the fourth question too. So it's like they're asking about the architecture, and we know it's just a von Neumann architecture because it just has a single SRAM. That's just so simple. Single SRAM is in von Neumann architecture. So now it's the fifth question. Elaborate register organization of microprocessing or controller element. We discussed about the register operations more clearly in the block diagram itself. We saw how the boot program was executed, the first program when the system boots itself. So we have uh, a start primary boot, uh, and when the bit 5 is set, bit 5 of the security register is set, then the contents of the OTP with the security register contents are copied to the base of the SRAM, which is there in the boot ROM. Okay, so and the program gets executed. Then, suppose if the bit 5 of the security register is not set, the boot then the boot happens according to the boot source pins, which is nothing but the modes, the different modes. So that did not happen. So we spoke about the security register, which is for the secure boot, disable JTAG, disable link access. We saw what's a JTAG. Hmm. So let's go to the next one. Disable global debug access. We just saw everything about what is a security register. And the sixth question, which is very easy. So they're asking the type of algorithm used for signed and unsigned calculations. Unsigned uses addition and subtraction. Signed uses is used for multiplication and division. That's so simple and easy. And the seventh one is also easy. Asking what type of control logic unit is used and correlate its performance with the type of control unit. So based on the architecture, it is hardwired and not microprogrammed. That's so simple. That was a direct question. In eighth question, they're asking about the memory management system of XS1 by XMOS. So instead of a slower memory subsystem with caches, the entire X core, which is the cores from 0 to 7 logical cores, memory runs at the operating frequency of the processing pipeline and is entirely deterministic. So we don't go out of the slower technique, and instead we run everything, all this 8 logical cores at the same operating frequency. So the task communicate explicitly with the external flash or SDRAM memory using IO ports. So the IO ports will be used to communicate with the SDRAM, and SDRAM SRAM memory is contained in all the tiles, X tiles. Okay, so which is shared between all cores and the tile for code and data. The schedule each scheduled core has an allocated slot to access that memory. Tasks communicate via inter-task communication channels, X-connect links and switches. We saw about the X-connect links, switches, and 32 channel ends. So the cores, logical cores communicate through the channel ends, which goes to the switches and all. And these are all connected by X-connect links. So each tile also has a block of one-time programmable memory for secure boot code and encryption keys. Spoke about the cryptographic keys also. In the ninth question, they're asking about the pipeline and parallel processing capabilities of the unit. So it has a four-stage pipeline, as we saw in the block diagram itself. We saw that the cores communicate with the four-stage pipelines. Two, yeah. So transfers to and from the pipelines and is synchronized with the execution of the input and output instructions or the port that can be configured to buffer the transfers and convert automatically between serial and parallel form. So synchronizers and ports and all are used in this four-stage pipeline. That's just simple. That's nothing complicated. And find whether the 10th question, that's the last question of this research which I've done. And 10th question, they're given find whether process level parallelisms available in the element selected. So yeah, we know as per our research, yes, the process level parallelism is available uh, using that the processor runs multiple tasks simultaneously using logical cores. Logical cores. So each of which is a guaranteed slice of programming power and execute computational code. Multiple devices can be employed and connected using an integrated switching network. So CAC coherence is in multi-core controllers is seen to be convenient as there are 7 cores, 0 to 7 cores. The main important feature of this microcontroller is the presence of 7 cores as an X core tile. So the microcontroller have more performance and it uses processor level parallelism is there and yeah, it enables more resources to be added to the design, so it's resource friendly and interoperability. So and easily we can code it with high level languages and all, so it makes um, things more easier. And that's all. Thank you. This is the end of the recording. And before I end the recording, uh, I've used so many tools to make this research presentation, and I would like to give a small introduction to the tools. I've just used draw.io uh, to make these block diagrams and all. Um, and even this, the main block diagram too. So I've used Photoshop to create the EPS format images and draw.io to make the block diagrams and all. And yes, these tools were so beneficial and useful. That's all about the microcontroller, and thank you.